All right. Well, greetings. I am Miranda McBride, and I'm the director of the Center for Advanced Transportation Mobility, also known as CATM. And I thank you for tuning in to this webinar. Today, I am very pleased to have Dr. Houbing Song, who is going to talk with us about transportation research that he has been conducting for CATM. Dr. Houbing Song is a tenured associate professor in the Department of Electrical Engineering and Computer Science at Embry-Riddle Aeronautical University in Daytona Beach, Florida. He is also the director of the Security and Optimization for Networked Globe Laboratory, also known as the Song Lab, which corresponds with his last name. I like that. And he received a PhD in electrical engineering from the University of Virginia in Charlottesville, Virginia in August 2012, and joined the faculty at Embry-Riddle Aeronautical University in August of 2017. Dr. Song has served as an associate technical editor for the IEEE Communications magazine and an associate editor for the IEEE Internet of Things Journal, IEEE Transactions on Intelligent Transportation Systems, and IEEE Journal on Miniaturization of Air and Space Systems. He is also a guest editor for several IEEE journals, including the IEEE Transactions on Intelligent Transportation Systems and the IEEE Internet of Things Journal, and as well as the IEEE Sensors Journal, just to name a few. There's several more that he is also affiliated with as well. Dr. Song is the editor of 8 books, and these include Smart Transportation, AI-Enabled Mobility and Autonomous Driving, and another titled Aviation Cybersecurity, Foundations, Principles, and Applications. So those are just 2 of his books that he has published. Additionally, he has authored more than 100 articles for which he has received several Best Paper Awards and received 2 patents. His research interests include cyber-physical systems, Internet of Things, cybersecurity and privacy, AI, machine learning, big data analytics, connected vehicles, edge computing, unmanned aircraft systems, smart and connected health, and wireless communications and networking. So Dr. Song's research has been sponsored by several federal agencies and featured by multiple popular news outlets. And we have the pleasure of learning more about one of these projects, which is titled Secure and Trustworthy Transportation, Cyber Physical Systems. Dr. Song, thank you again for joining us, and the floor is yours.
Thank you, Dr. McBride, for your introduction. I'm very glad to give a talk entitled on secure and trustworthy transportation cyber physical systems in the Transportation Innovation Speaker Series hosted by Center for Advanced Transportation Mobility, USDOT. So here, this is my outline. First, I will introduce myself since most of you don't know me well. Then I will talk about my lab. After that, I will talk about what motivates me to conduct research on transportation. After that, I will talk about 2 representative projects. One is real-time machine learning for quickest event detection. The second one is trustworthy transportation, cyber physical systems for real-time prediction. After that, I will talk about ongoing research in my group. In the end, I will give a summary. So here, I'm not a pure transportation guy, but I have some background in transportation. So in fact, my background is multidisciplinary. I have 1 bachelor, 2 masters, and 1 PhD. In fact, both master's degrees are related to the transportation. For the first master in electrical engineering, you can see my master's thesis title is Dynamic Traffic Assignment and the Estimation and Prediction of Dynamic Origin Destination Flows. It's about intelligent transportation system. The second master is in the civil engineering. I did this at the University of Texas at El Paso. The title is the Development and Calibration of the Mesoscopic Simulation Model for the Vehicular Traffic Modeling. So in fact, after I received my second master's degree, I joined the Texas A&M Transportation Institute as a engineering research associate. In fact, recently, I'm very active in the community of HRE transactions on intelligent transportation system. I'm serving as a associate editor for this transaction. In fact, I found 3 interesting rankings about me in this HRE transaction. I'm the top 30 most published author in this HRE transaction on ITS. It's a lifetime. I'm 50th, the most cited author in this transaction, also lifetime. In fact, one of my papers on transportation is top 80, the most cited paper in this transaction. So this is author rankings from exactly.com. If you are interested, you could refer it. So now I will talk about my lab. You can say my lab is named after my last name. In fact, here, each letter has its own meaning. So for my lab, the main thing is to advance the research and education through the discovery and innovation at the confluence of 3 areas. The first one is AI, machine learning, data science. The second one is cybersecurity. The third one is computing-enabled network physical system. Intelligent transportation systems is one system like this. So here, as denotes the security, I conduct research on the cybersecurity, cyber-physical system security, physical security. In fact, I'm very interested in detecting everything. I want to detect the threat, intrusion, vulnerability, anomaly, models like that. Here, the optimization. I'm really interested in the several the optimization criteria like the speed. I want to optimize speed, accuracy, reliability, security, cost. I want to know cost. So here, the technique. Like AI, machine learning, data science, analytical signal processing, and control, such like that. Here, energy, the network delay. So I conduct research on Internet of Things, networking, Internet of Vehicles, such like that. So using, the IPS is one application, the network.
Dr. Song, we're having some difficulty understanding you. The audio is very muffled.
Okay.
Yeah, it started off a little muffled, but then it cleared up, but now it's muffled again.
Okay. How about now?
It sounds like do you have multiple, is there a microphone or something that's picking up some of your audio? It sounds like there's a lot of reverberation.
Okay, I just turn off all audio devices. Just leave, my laptop now.
Okay, yeah, that sounds good. That sounds
okay.
Good.
Thank you.
Sorry for interrupting.
Okay, thank you. In my group now, I supervise 8 PhD students and 4 master students. In fact, I'm very proud of my recent PhD graduates. Last year, I graduated 3 PhD students. All of them have been hired as tenure-track assistant professors at U.S. universities, like Bowling Green State University, Auburn University, University of Tennessee, such like that. Also, 17 master students graduated from my group. So my group, since our group it's very big, we have many students. We publish a lot. We published more than 100 papers in actually ACM transaction journal magazines, more than 50 in conferences. Also, we opened the file code and the data set through actually DataPart and GitHub in case someone is interested in our research, they could try. Through the ACM Distinguished Speaker Program, I have 4 lectures available. I give talks very frequently across the group. Due to the COVID, most talk is just virtual, like this webinar. So also I had 2 patents granted. So in fact, based on the for the research impact, based on the citations, our paper have been cited by more than 20,000. Its index is like 72. Also, for the scopes, it's more than 13,000. Its index is 61. Web of Science, it's more than 10,000. Its index is 55. So due to the high citations, I was ranked as a highly cited researcher last year by the Web of Science. Also, according to the research.com, I'm a top scientist in the field of computer science. My ranking in the US is top 1,000. Also, I'm the world's top 2% scientist list prepared by Stanford University based on my career-long impact and single-year impact. So we received 11 Best Paper Awards in the past 3 years. Also, we edited several books. Related to transportation, like one is smart transportation, AI-enabled mobility, and autonomous driving. So this one is related to our CETM center. Also, secure and trustworthy transportation cyber-physical systems. Also, for the smart cities, the transportation is one part of smart city. In fact, for this book, has been highlighted by the Actuary Explorer, this database. So now I want to talk about my motivation for the transportation research. In fact, for the transportation, we are facing a lot of challenges, basically 3 categories. The one challenge is the safety challenge. Each year we have the US has 37,000 deaths due to the transportation accident. Crashes each year is like almost 6 million crashes. The economic cost is like $230 billion per year. It's a lot. For the mobility challenge, each year we lose 4.2 billion hours. Also, we waste 2.8 billion gallons of fuel. Also, for the economic cost, it's like $87.2 billion per year. Also, it's a lot. So for the environment challenge, each year we have the 2.8 billion gallons of fuel wasted. In fact, 22% of CO2 emissions from the vehicle. It's a lot. It's a high percentage. So here also, we have challenges in other sectors. Today we don't care about this. So since this is transportation webinar, so to address these transportation challenges and other challenges, we need more responsive, precise, reliable, and efficient systems. Such systems are called cyber-physical systems. So according to the National Science Foundation, cyber-physical systems are defined as engineered systems that integrate cyber components into physical objects and infrastructure, and then connecting them to the internet and to each other. So here, cyber components include, basically we have the 4 cyber components like sensing, computation, control, and networking. So here, everyone knows, the internet transformed the way people interact with the information. But now the cyber physical systems are transforming the way people interact with the engineered systems. Transportation system is one, the engineered system. So here, let's see the first cyber component. It's sensing with a different, as we are using, smartphones, iPhones now. In fact, there are many sensors in our smartphone. So in fact, we use sensors to connect the information about our environment. So here is about our transportation system. So the second cyber component is computation. Now we are in the era, it's big data. So here with the big data, we could do the modeling, simulation, and optimization. So here we could collect the large scale data and do the data analysis and management. So also we could control and manage, our transportation infrastructure. Also, we could make the dynamic and intelligent decision making. Also, before that, we could model the complex transportation systems. So the third cyber component is control. So now we are in the third generation of control. So it's called the networked embedded control. This one embedded, in fact, is related to the sensors, because most of the sensors, not like our smartphone, many sensors, some just embedded in our smartphone. So this is called network embedded control. So the fourth, the cyber component, it's networking. So Internet of Things. In fact, it's the networking infrastructure for cyber physical systems. I just mentioned the sensors. If we connect our sensors together, so it's called the Internet of Things. So we need the sustainable, high speed, high capacity, and energy efficient networking to support transportation cyber physical systems. So here, but problem is here. Now there is no mature science to support the systems engineering of high confidence cyber physical system. This is one problem. Another one is for the cyber physical system, they are subject to cybersecurity threats. So, the tomorrow is beauty, but without, the security and the safety, we can't achieve, the CPS enabled vision of the future. So we need to address two fundamental problems. One is how can we design, build, and verify reliable, predictable, safe, and secure cyber physical system. The second question is we need to address how can we develop a strategy and technology to respond to the cybersecurity threats. So this is, two fundamental questions. So why are these challenges are so difficult? One is the cyber CPS design and verification, deep interdependencies between cyber and the physical component. Another is we propose the greater, higher requirement for the safety and the security. Also, scalability and the reliability. The second reason is CPS security. CPS, cyber physical systems security, sometimes, human in the loop. We need to consider the human factors. So here, the cyber physical systems design and verification and the CPS security, we need a multidisciplinary efforts. So we need the integrated perspectives. So here, for my group, we focus on the ITS research in the age of AI, machine learning. So for the transportation related research, I just want to address this fundamental question. How can we design, build, and verify reliable, predictable, safe, and secure intelligent transportation system and beyond, like autonomous systems and other the cyber physical system. Here for transportation, we want to enhance safety, mobility, and environmental sustainability. From the title of our center, mobility is there, right? So in fact, for the transportation, I care about mobility and safety and the environmental sustainability. So I focus on the AI machine learning for intelligent transportation system to several sub areas, include the real-time traffic prediction, real-time machine learning for quickest event detection. Sometimes if we don't have the big data, we still need the the good performance. This is called the data efficient machine learning for detection if we don't have big data. Also, secure and trustworthy transportation cyber physical system. This is the title of my talk today. Also now, electric vehicle is popular. So I care about electrical vehicle charging management. So this is my focus. So now I will talk about two representative projects briefly.
The first one is real-time machine learning for quickest event detection. So in fact, this one is a broad transportation. We start from the aviation. So in fact, this is 3 years ago, in the summer of 2019, I was reported by HRE as a hacker. So this made me in big trouble. So they said, the new technology hijacks intrusive drones. A professor from Florida's Embry-Riddle Aeronautical University has developed a system for overtaking unauthorized drones without downing or destroying them. So the big trouble is here. More than 100 news media outlets, they report me as a hacker. So in fact, the total potential audience is like, 16 million people. It's like every 20 people in US, they know me, I'm a hacker. So actually global spec. For Focus TV, they reported Embry-Riddle team developed the hijacking technology. Secure Magazine, this is just for the executives. Florida professor invents AI program to hijack drones. So US News and World Report. Also, Association for Unmanned Vehicle Systems International is another association. Also, New Atlas. Also, some military news outlets like Battle Space and the Defense Delay. So this is, this news made me in trouble. So now let's see. In fact, my motivation is very simple at that time. So due to the increasing UAS sightings near airports, we don't like this. So for UAS, the full name is unmanned aircraft system. Also, we can call UAV unmanned aerial vehicles, or simply just drones. As we don't like the drones to fly near airports because there will be collision risk with manned aircraft. So also we don't like the drone fly in and around the stadiums, the sports events, because too many people on the ground. So also we don't like the drone to fly over the national security sensitive facilities, like military bases, like national landmark, like White House, like the Howard Dam, like Statue of Liberty, such like that. Also for the certain critical infrastructure, nuclear power plant, we don't like the drone to fly near. Also sometimes when we conduct the emergency and rescue operations, in our CTM, emergency is in our title. So when we conduct the emergency operation, we don't like the drone to fly near, because this will interrupt our normal operations. So like emergency, like wildfire, hurricane, such like that. So this is the motivation. So there is a clear need for the counter unmanned aircraft system. So such a system is defined as a system or device capable of lawfully and safely disabling, disrupting, or seizing control of an UAV. So here, such a system, typically, we have two subsystems. One is the detection subsystem. The other is the response subsystem. For the detection subsystem, we need this subsystem detect multiple drones at a distance and support highly automated operation. For the response subsystem, we want to disable or destroy multiple drones at a distance. At the same time, we want to make sure the damage is low, the cost is low. So why I was reported as a hacker appeared in many news outlets? Because my system is unique. I'm a hacker, but I hack just for good. I don't do bad things. So my uniqueness is like that: we detect and safely neutralize rogue drones without destroying them or causing them to crash. So this is unique. We don't need to shoot down the drones. So in fact, for my system, also it's two subsystems. for the detection part, it's in fact we use the machine learning enabled real-time detection. Here we use the Internet of Things. So in fact here we use acoustic things. So we detect the zone. After that, probably we want to know the ID of the zone. We call identify. After that, probably we want to know the precise location of the zone. We call the localize. So this is the first subsystem. For the second subsystem, it's a response subsystem. Here we use the software-defined radio transceivers. Here, our uniqueness, like we are hackers. We hack. We in fact hack. It's decode. We decode the radio channel. It's a frequency band the zone is using. Then we decode the modulation mode the zone is using. And then we decode the protocol the zone is using. With the decoded information like radio channel modulation mode and the protocol, we could generate fake control command. And then we send the fake control command to the zone. The zone doesn't know this is the command, it's fake. They just follow our fake control command to fly away, the sensitive areas. So in this way, we don't need to destroy the zone. So this is, our uniqueness. Here is a picture. The smallest circle is a sensitive area, like White House, like, the airport, like, the stadium, such like that. The largest circle is a detection area. Here we deploy microphone arrays. Also, we call Internet acoustic sense. We detect if there is a zone approaching or not. The middle circle is a reaction area. Here, we need to take action. We need to guide the zone fly away. So this is reaction area. We want to avoid the zone to fly into the sensitive area. So here, for my system, on the top is a detection layer. We collect the acoustic signals, and then we perform the pattern recognition, and then we check if this zone operations is authorized or not. If it's, we estimate the presence and invoke the reaction layer on the bottom. For the reaction layer, if we recognize this is an authorized zone operation, we will scan the radio channels, the frequency band, and perform the spectrograph analysis. Then we will identify the control channel. At this time, here we will send the warning information to the zone. You are not allowed to fly here. You need to leave. If the zone doesn't follow this warning, so we will block the zone's channel to trigger its returning strategy. The zone will just return to its original location. Then if this doesn't work, we will try to identify the protocol, and then we will transmit, our fake control command. So if this doesn't work, probably we have to shoot down. So, but basically before that, we could address this. So here for the detection part, in fact, it's 3 steps. It's 2 steps. The first one is acoustic detection, identification. Probably you want to ask why you use acoustic. Because here you can see in the middle, there are 4 pictures. One is the natural background. The second one is a heavy rain. Also on the bottom, the 2 different types of zones. You can see the power spectral graphs. They are totally different. So if you know the signal processing, we could use filtering to detect if this is a zone, not a bird, not any other objects. So this is our why we use acoustic detection. The second step is localization. As you can imagine, with 3 or more microphone arrays, we could localize a zone. So for the second part, it's a response subsystem. So 3 steps here. We identify the radio channel frequency band. We identify the modulation mode, and then we identify the protocol the zone is using. So here, the performance detection. Here we collect the data 25% is a sound of test zone, 25% the data is from heavy rain, 25% is from natural background, 25 is just random noise. Then we select the 50% as the training set, the 30% as the test set, and the rest is 20%. Then we conduct the vectorization. In fact, we use faster frame transformation, and then PC principal component analysis, one technique in big data analytics, and then SVM support vector machine, and then we conduct the performance evaluation. So also here it's our result for the protocol identification. We consider different combinations like random, multi-way, UV talk. Also, we consider two different scenarios. One is the x-axis, it's the dimensions. The other is the beta error rate. So also we conducted a field test in Daytona Beach Radio Control Association. So we did a successful field test. So after that, I have the big trouble from government, military, and industry. The United Nations, they approached me. There is one agency in the United Nations. It's called the International Civil Aviation Organization. They asked me to provide some suggestions, guidances on how to, counter unmanned aerial vehicles. Government, like in fact, within 1 week of the news media outlet, the director of the Office of National Security Programs within Federal Aviation Administration visited Embry-Riddle. That guy asked me to give him a demo. So in fact, after that, he gave me several projects, sponsored me several projects, like the UAV cybersecurity, safety risk, and the mitigation for UAV operation on and around airport. Also, industry attentions a lot. The big companies are like Boeing. Boeing, manufacture, the manned aircraft. But in fact, they have, one program. It's called the integrated vehicle technology. They care about unmanned aerial vehicles. Boeing asked me to lead one consortium consisting of 6 universities to pursue one funding from the NASA. It's called University Leadership Initiative. Also, one big company, Cameron Sensors and Electronic Systems, is a top 25 company listed in London Stock Exchange. Also, SRC, Syracuse Research Corporation, they asked me to collaborate with them. Also, military. So, like the Air Force Research Lab, Defense, DARPA, Defense Advanced Research Project Agency, DTRA, Defense Threat Reduction Agency, U.S. Special Operations Command, and the U.S. Central Command. They asked me to serve as a SME, subject matter expert. So here, I identified one scientific problem. It's called the real-time machine learning for quickest event detection. I found, they are very care about, some event, specific event, depending on their need. Probably it's a threat, vulnerability, and intrusion. So also they posted several specific challenges. The first one, they care about performance, detection performance. One is accuracy, the other is the latency. The second specific challenge is how to explain why. Sometimes they ask me why your approach works well, why other approaches didn't work well. So they ask me to explain why. The third specific challenge is how to achieve the good performance if no big data available. Sometimes, people are greedy. I don't have big data, but I still want the good performance. Can you do that? So this is, the third, the specific challenge. So to address this, the challenges, I set up, my long-term goal for my group. We want to establish a framework for machine learning enabled event detection applicable to multiple domains such as ITS. So I focus on the 4 areas. The first one is a mathematical method for deep learning. This is for explaining why. If we want to explain why, we had better start with mathematics. So the second area and the third area is one is accurate detection. The other is the quickest. Accurate detection is for the accuracy. Quickest unit detection is for latency. So these two are for our, the first challenge. The fourth one is data efficient machine learning for unit detection. This is for if we don't have enough data, can you do that? So this is my basic, the long-term goal. So today I just, ignore, the technical details about this research. I just want to mention one breakthrough incremental learning. Last weekend, I just reported this to DOT. In fact, this one is very interesting. Our lab discovered and proved the role of rotating memories in enabling AI. What's the rotating memory? The rotating memory, it's like, we learned, when we learn something, we learned something. We just want to leverage, the previous knowledge in our new learning. So, because, for some real-time systems, we don't want to, learn from scratch each time. So we want to leverage the old knowledge. But, when the new data comes in, how to integrate the new data with the old knowledge. So this is, here we identified if for the new knowledge, the new data and the old knowledge, they are orthogonal, 90 degrees separate. So the learning performance will be the best. So this is very interesting. We provide one mathematical proof about this. In fact, I'm very excited to find this for the Princeton University. One group of neuroscientists, they found the same phenomenon as ours. So, but they used a different way. They conducted mice experiment, at least for mice. If you change, the separate, the old knowledge and the new data, 90 degrees separate, the result will be the best. So neural representations of sensory information gets rotated 90 degrees to transform them into the memory. In this arrangement, the memories and the sensations don't interfere with each other. Someone, we also received a lot of media coverage. Some called revolution of AI model. Probably this is the revolution of AI models. In fact, probably you know this. Cross writing. This one, in fact, I think the human beings are very smart. In fact, for our idea, rotating memories, in fact, it's corresponding to one, the activity we used almost 200 years ago. So here you can see this is one example of cross writing. So here at that time, people are very poor. We want to include more information on one paper because at that time it's very hard to get a paper. But how to save the paper? Here, how to include more content in one paper. You could write, line by line, and then you could write, column by column. So in this way, if, lines and columns, it's just 90 degrees separate. You can still read, the word, right? If you use the different directions, it's not clear. So this is like 9 rotating memories. So it's very interesting. So if you are interested, interested in this, you could see our the proof. Also, you can see the Princeton's, see there, the research findings from their mice experiment. Also, cross writing. So here, this is the first one. The second one, I will talk a little bit briefly. So here, it's a trustworthy transportation cyber physical system for real-time prediction. So in fact, now for the transportation cyber physical system, the networking infrastructure, in fact, it's a vehicular ad hoc network. Also, we can call connected vehicles. Basically, for this network, we have two types of communications. One is the vehicle-to-vehicle communication. The other is the vehicle-to-infrastructure communication. We can call V2V and V2I communications. So here, this is in the center is a car. We have DSRC. It's dedicated short-range communication, vehicle-to-vehicle. DSRC, vehicle to roadside. DSRC, vehicle to hotspot. Satellite to vehicle is GPS. We use this every day, I believe. Vehicle to the cellular. Also, here on the right bottom, it's a traffic management center. So this is network infrastructure for the transportation cyber physical system. So in fact, like weather forecast, every day before we leave, we need to check the weather to decide what to wear, right? In fact, for the traffic estimation, it's similar. Before we leave, we want to know which transportation mode we take, which route we take. So this is traffic estimation. You can see the importance. So here we face, we want to convert, the data to the real-time traffic prediction, and then we could make the optimal decision. So here, in this way, for the transportation DOT, they could, facilitate effective traffic management. For us, we could, make sure our arrival is timely. So pre-trip, we could decide our depart time, mode choice, route choice. On the way, we could change our route to avoid, the congestion, such like that. So here, our work is a simulation-based real-time traffic prediction. So in fact, we simulate for the transportation. The one big problem is, between the supply and the demand. So here on the top, we have the surveillance information. We have the parameter values. Also, we have historical data. And then we put this data into our simulator. For our simulator, we have two parts. One is the demand simulator. The other is the supply simulator. In this way, we could estimate the state. Then we conduct, the model calibration. After that, we could conduct the data prediction. After that, probably every several minutes, we need to run another loop. So we will go again. So here you can see accuracy depends on the calibration. So for our work, so in fact, we formulated the state space model for the online calibration. So here we define the state vector. We introduced the idea of deviations. In this way, we could incorporate as much historical information as possible. So we have the new state vector. Here for the output vector, we have direct and indirect. So on the bottom is our state space model. We have transition equation and the measurement equation. So here, with the notations like this, we can get the classical state space model like this, transition equation and the measurement equation. So here, this is our performance evaluation result. We use the data from I-80 freeway database provided by Federal Highway Administration. Our research findings published in the Transportation Research Part B and the TRB annual meeting. So also, in fact, I have the one demo available at YouTube. If you are interested in this, you could click on. Here, the second part is the trustworthy part. So here for the real-time traffic prediction, if this is true, we will have smooth transportation. But if this is false, probably we will have, traffic congestion. So here it means, for the big data security and the trustworthy, it's very critical. So here, let's say for the, we deploy a lot of sensors in our transportation system. So let's say the sensor node in transportation CPS. Typically two types. One is the onboard unit, OBU. The other is roadside unit, RSU. So here for the node, sensor node, typically we have several types of misbehavior, like probably the sensor doesn't work, it's faulty. Probably we have hackers. It's a malicious. So here it's intentional. We have different attacks, here, like a simple attack or bad mouse attack or zigzag, such like that. So here from this picture, we can start with the sensor node 1. Here we have incoming packet and then dropped. For the second one, we have the incoming packet. For the outgoing packet, it's different from incoming. Here, packet modified by attackers. So the third one is denial of service attack. So here we could send many dummy data just to occupy the channel. In this way, others can't use the channel. So that's the three, the attacks. So here, for the traditional security solutions, we could, use different misbehavior detection like IDS, intrusion detection system, or cross-layer detection or routing detection. Also, we have the trust management, like confident and core. So here, let's see this picture. So here, for this transportation cyber physical system, we have, the different node 1, 2, 3 to 6. If we use the misbehavior, probably we find the node 1 is misbehaving because this sensor drops packet. If we use the trust management, node 1 it's not trustworthy because it's a drop packet. If we use the context awareness, nodes 2 and 4, it's just they are one's neighbor are busy sending packet. The question is node 1 really malicious or not? We don't know because from these three different mechanisms we get the results. Probably it's not consistent. So here I propose the holistic solution. We combine misbehavior detection, trust management, and the context awareness. We want to get a consistent result. So here, three components. Machine learning based misbehavior detection is on the top. Also modeling node trust as a vector trust management. The third one is context awareness. So here, probably we could get a result like this. The busy channel for node 1. Here, why the busy node 1 is forced to drop packet, but it's not malicious. In this way, we could trust node 1. It's trust once trust gets punished less. So here, the first part, basically traditional we just use stress-based misbehavior detection. The challenge it's very hard to decide the weight and the threshold manually. So here we introduced the support vector machine for automatic operations. So the second part, modeling trust as a vector. Traditional is just a scalar. It's sometimes we are not clear. So we introduce the vector approach. So we will get a vector. So the third part is context-aware policy management. So here, for these two scenarios, is node 1 equally trustworthy in both cases? In fact, probably yes, according to the traditional mechanism. But in fact, actually it's no, because the context we need to consider where the context where the packet dropping occurs. So here we propose a 2D attack resistant trust management in transportation CPS. So here we collect data from vehicular ad hoc networks, get traffic data, and then we did do the data analysis. From the evidence we could establish our trust management establishment and management. So here the 2D means that we have the data trust and node trust. Further, for the node trust, we could consider functional trust and recommendation trust. So here, this is our performance evaluation. We can find our effect of node density and the impact of attack pattern. Our result is published in the actually transactions on ITS. This one is number 79 ranked paper in HRE transaction on ITS lifetime. So here I want to mention my ongoing research. So here the first area is AI machine learning for ITS. I want to use AI machine learning to enhance transportation safety, transportation mobility, and environmental sustainability. So we conducted real-time traffic prediction, real-time machine learning for quick event detection, and data efficient machine learning for detection, and electrical vehicle charging management. The second area is cybersecurity of ITS and beyond. We want to guard the ITS from the unintended uses and some exploitation by leveraging cybersecurity practices. So here, anticipated contributions from our research, I believe, lies here. The first one is travel behavior and transportation system modeling. The second one is environmental vehicle technology and fuel. It's an electrical vehicle. The third one is the climate change, air quality, and the other environmental impacts. So here, today I mentioned, I talked about my research theme. I talked about the fundamental question I want to answer. How can we design, build, and verify the ITS and beyond to enhance the safety, mobility, and environmental sustainability? Also, I talked about two representative projects. So several references about my two projects is here, ITS, cybersecurity, and AI. So here is references for my open source data set and code. If you are interested, you could download and try. So thank you. Any questions?
Thank you, Dr. Song. That was a very intriguing presentation. Hold on just a second. I had a question here. Yes, in terms of the video being posted, it will be posted on our CADM website. Let's see if I can.
Yeah, definitely. I would like more people to view it. Yeah.
Yes. So if because I was trying to get into my email, or it's because I'm recording, it's locking me out of being able to access the website URL. Debbie, are you able to go in where the video will be posted and post that link here in our chat so that people can obtain it efficiently? Okay, thank you. But thank you, Dr. Song. This was very interesting information. I was definitely taken aback when you were talking about getting in trouble for some of your hacking processes. So I'm kind of curious, when it comes to what you're doing, is there any type of permission that you typically have to get in order to be able to conduct some of these studies that essentially are considered to be hacks? Is there some sort of approval mechanism that you often have to go through, or is that usually after the fact?
In fact, this one is very interesting. I'm teaching the cybersecurity courses here. Mm-hmm. We have the one lab. In fact, the cybersecurity lab is isolated from the internet. So this means, if we conduct attacks in our lab, this is doesn't affect the internet and the outer environment. For the research purposes, this is totally fine, because our lab is designated by the DHS, NSA, Department of Homeland Security, and the National Security Agency. So as you know, probably this year, I think for DOT, for the new round of center computation, this just the first time they include transportation cybersecurity into the topics. So I'm very glad, we have did something before that. Yeah.
Yeah. I think it's becoming more and more important as we move into more AI-enabled transportation devices and infrastructure. There's several lay people, of course, who are concerned about that security mechanism. And the fact that, you know, seeing some of the work that's being done definitely helps kind of assuage some of that concern. But of course, you're one of the good guys.
Yeah,
One of the
in
bad
fact,
guys
you
actually
can
doing.
you can say we have several books before that, you know,
Yeah.
already, yeah.
Yeah. So let me see if there's any questions. It looks like in the chat, thank you for the presentation. Cybersecurity related EVs is of great interest. Excited to see what is to come. Thank you, Bridget or Ms. Gilmore. I appreciate that comment. Are there any questions from the audience? Any questions or comments? I'll try to read any that pop up. So I was curious, Dr. Song, so you have, how is this? Greetings. Thank you all for attending this webinar, which is hosted by the Center for Advanced Transportation Mobility.
Oh, I don't know.
I'm not sure where that is coming from.
Director of the Center for Advanced Transportation Mobility, which is a Tier 1 university transportation center funded by the U.S. Department of Transportation.
Okay, it's gone now. I don't know where that was coming from. Looks like we were.
It's the CADM channel, but I was on mute.
Oh, well, I guess
But
your
is it
co-host
playing-
somehow or another, it just
Is it
projected
playing
itself.
from the chat?
It's possible. I don't know all this technology. That's we don't know exactly what it is.
Probably we are hacked by someone.
That is possible. That is very possible. But Dr. Song, I was curious, how is this technology deployed? So for the drone hacking, quote unquote, how is it deployed? Is there a device that people in an emergency, let's say if it's an emergency response team and they want to make sure there are no drones that are inhibiting their capability to perform their function, how would they deploy this device? What would it look like in their hands?
In fact, this is just a low-cost device. We could deploy, you know, if we want to deploy around the airport, we could deploy, you know, on the ground. So in this way, it's like, you know, a circle. We could deploy, you know, the several devices like this. When the drone, you know, the enter or close to the, you know, the circle, we will detect it. In fact, you know, this we filed 2 patents. So the one small, I think the start processed our technology. They are commercializing our technology now. Yeah.
Okay. And you said you have the United Nations, FAA, military, Boeing, and other industry partners who are interested in seeing how this advances. Several of them have been funding additional projects. Is that correct?
Yes. Yeah. In fact, now recently I just signed one teaming agreement. It's for the NASA. So they want to pursue a very big grant. It's like the $46 million. So I'm not sure if we succeed or not, but we just signed the agreement. Yeah.
Okay. So where do you see this going in the near future, like in 5 years? Technology keeps changing. How do you manage to keep up with this changing technology? Because you have to be able to, your software, for instance, has to be able to detect the device, the drone itself. Then it has to be able to go in and actually in some way manipulate its programming, it sounds like, the protocols. So how do you go about keeping up with all this changing technology?
In fact, now our current plan is like we need to develop the products, you know, based on the generation. So now we are planning to, you know, for the first generation product. I believe probably every 1 or 2 years, at most 2 years, we need to, you know, update the product for the second generation. After that, we need to continue to, you know, update based on the new technology. You know, we decode, you know, the information because, you know, for the new zones, probably they want to avoid being decoded. So we need to consider this. Yeah.
Okay. And even with when you were talking about the secure and trustworthy element of your presentation with the sensors and the malicious attacks, So it sounds like that what you're doing is you're combining those three different mechanisms of detection. Is there any priority set in terms of determining how to ultimately classify an event? So if you have those three classification mechanisms and maybe two of them are indicating a malicious type of attack and one is not, does any one take precedence over another in your programming?
In fact, here, no, we just want to make, these three different approaches until one consistent result.
Okay.
So, if something's not, consistent, we need to, try again. We need to get the, one good result for this.
Okay.
In this way, we could take action. Yeah.
So are the three mechanisms or the three classification systems that you mentioned, are those the only ones, or are there others that would need to probably be or might later on be taken into consideration?
Yes. Yeah.
There are others. Okay. Okay. All right. Are there any questions from the rest of the audience? All right, well, Dr. Song, I greatly appreciate your presentation. It was very interesting. We will get it posted on our CADM website. So those who may not have been able to attend, I'll send out the link to our distribution list to make sure that they have access to it as well. So can you go back to your last slide with your contact information? So that way, if anybody wants to reach out to you, they'll have that easily accessible before we sign off.
Yeah, my email is very simple.
Yeah.
Song@computer.org.
All right, so if you want additional information on the work that Dr. Song is doing, please feel free to reach out to him. Of course, you can also reach out to me at mcbride.ncat@ncat.edu, and I will make sure you get directed to the right person. But thank you for viewing this presentation. And Dr. Song, again, we appreciate your time and all the energy that you are putting into making sure that our transportation systems are secure and trustworthy, because that's an important element going forward. All right, take care.
Thank you. Yeah, have a nice day.
You too.